Thanks so much for the introduction and for the invitation to be here. Yeah, very much looking forward to the discussions this upcoming week. So yeah, the title of the talk is Estimating Magic and Other Properties. So the topic of this talk is more of kind of a quantum learning theory bent, but I hope one goal of this presentation will be to serve as kind of an invitation to members of this community to maybe think about or revisit some of the foundational questions in quantum learning that sit at kind of the periphery of quantum simulation. Okay. And so the starting point for most of today's talk will be this question that many of you are familiar with of shadow estimation or shadow tomography. This is a task that was put forth by Scott Aronson several years back, and was meant to provide kind of a scalable alternative to the classic question of full state tomography, right? Where you want to actually do interesting things for n qubit systems without having to pay exponentially net. Okay? And so the question, just so we're all on the same page, is as follows. You're given copies of some unknown quantum state. You're given a bunch of observables that you care about, O1 through OM. And your goal is to estimate these observable values up to some additive error. And so the point is that you want to sidestep this issue of outputting a full classical description of the state and instead just try estimating properties of the state. And it turns out that this simple kind of shift in perspective introduces a lot of interesting algorithmic and statistical subtleties. So two use cases that I'll focus on for today's talk. The first will be that of energy estimation. So say you're running some variational method, and you actually at some point have to compute trace of H rho for your candidate state rho. A couple years back with VQE, we saw that one way to do this is to compute the Pauli decomposition of your Hamiltonian of interest and just try estimating Pauli observables of your underlying state, and then stitch together these estimates to get an estimate for trace of H rho. Okay, so this is a task that by now I think sometimes goes by the name of Pauli shadow tomography, and this will be the focus for the first part of today's talk. And the second use case is that of quantifying resources, for instance, magic. Okay? So even from the perspective of Pauli shadow tomography, nowadays there are various ways of quantifying the extent to which your system can be classically simulated using quantities like Bell magic, stabilizer entropies, what have you. You can think of these as a form of magic that involves taking a functional of this Pauli spectrum consisting of all of the Pauli observables of your state. And apart from these functionals of the Pauli spectrum, you can also look at distance-based measures of magic. Okay? So one canonical notion is that of stabilizer fidelity, which simply says, okay, I want to figure out how classically simulable my state is. Let me just look at the closest stabilizer state, let's say an infidelity, to my unknown state rho, and let me try approximating this fidelity. Or better yet, let me try approximating the argmax of this expression, so the actual closest stabilizer state. Okay, so this is the second use case that we'll think about in today's talk. Okay, so let me just briefly recap what's known about shadow tomography. Of course, if the observables actually commute, then things are simple, right? I just measure in the joint eigenbasis that simultaneously diagonalizes these observables, and just by a simple Chernoff and union-bound argument, you find that log m over epsilon squared samples are necessary and sufficient, where m is the number of observables and epsilon is your target precision. Okay, so this is the best one could hope for, and you can achieve this when the observables are commuting. But of course, when they're not commuting, the uncertainty principle limits how much information you can hope to extract from a single copy of the state. Okay? So this is really the key challenge behind shadow tomography. But this very nice line of work that emerged from sort of the theoretical computer science community established that actually for this task, despite the uncertainty principle, you can actually hope to get close to this log m over epsilon squared rate, even for non-commuting observables. Okay? So this line of work that was initiated by Scott Aronson has now shown that there are protocols that can actually estimate all of these observable values using a number of samples that only scales polylogarithmically in the number of observables you care about, m, polynomially in the number of qubits, or logarithmically in the Hilbert space dimension, and inverse polynomially in the error. So this is great. But of course, all three of these parameter dependencies are potentially suboptimal, right? This is still a far cry from this log m over epsilon squared gold standard. Unfortunately, the protocol also requires a huge amount of quantum memory, right? So in order to measure many copies of the state at a time, and it's computationally efficient, at least as presented, because it requires some form of Gibbs state preparation. Okay? So as we all know, there's this beautiful resolution to some of these issues by Robert Huang, Richard Kuhn, and John Preskill a couple years back, this framework of classical shadows that managed to kind of sidestep all of these issues of computational inefficiency, large quantum memory, and suboptimal statistical complexity in, for some important classes of observables, namely few body observables, bounded rank observables, more generally observables of low shadow norm. And amazingly, they only use single copy measurements. Okay? So how you should think about today's talk is I'm going to describe some use cases where you need to go beyond this kind of classical shadow framework, but the sort of core algorithmic challenges for the problems I'll describe are firmly rooted in some of the most basic difficulties behind shadow tomography. All right, so just as a kind of roadmap for the rest of the talk, I'm going to talk about a pair of works. The first will be on estimating Pali observables, and this is based on joint work with my student Weiyan Gong and Qi Ye, who is a visiting student at Harvard and is a PhD student at Tsinghua. Okay. And in the second part of the talk, I'll then turn over to this other use case of quantifying resources and specifically estimating magic as measured by stabilizer fidelity. And this will be based on joint work with the same set of students, plus Zhihan Zhang, who will be a PhD student at Caltech starting this fall. Great. OK, so let's get started. So just so we're on the same page, the focus for this part of the talk will be on shadow tomography when the observables are n-qubit Pali operators. OK, and this kind of abstraction shows up in a lot of places. You can also think of it as like a nice kind of quantum version of estimating the Fourier spectrum of a probability distribution if you come from more of a classical background. But for me, I find this question particularly interesting because it provides a very clean test bed for probing what are called quantum memory sample trade-offs. Okay, so roughly speaking, these are trade-offs that try to quantify the extent to which having extra quantum memory and SILAs to perform your measurements can actually drastically decrease the number of samples you need for your learning task. So at the extreme, if your device is rather limited, maybe you're only able to measure one copy of your state at a time. And these algorithms end up being weak theoretically, but practically the kind of dominant paradigm for measurement. And at the extreme, you can imagine very powerful measurements that can measure all copies of your state at a time. These obtain optimal theoretical guarantees, but are practically quite challenging to implement. And there's an entire spectrum in between this. And I really like the fact that this Pali shadow tomography task actually allows us to access kind of this whole spectrum and understand the optimal amount of data you need for this learning task at any point along this axis. OK, so let me just briefly recap what's known about this problem. So a few years back, joint with Jordan Kotler, Robert Huang, and Jerry Lee, we showed the following kind of proto-memory sample trade-off. Okay, so we said for this Pali shadow task, if I want to estimate all Pali observables, all 4 to the n Pali observables, if I'm allowed to measure 2 copies at a time, I can do this very efficiently with just n over epsilon to the 4th samples. Okay? But if I'm only allowed to measure 1 copy at a time, then I need exponential in the system size. Okay? There is a caveat I'll return to, which is that actually this first bullet point, we were only able to estimate the absolute values of these observables instead of the true values. Okay. But the main upshot from this result was that with just a small amount of additional quantum memory, enough to measure 2 copies at a time, there is really an exponential statistical advantage over algorithms that don't have any quantum memory. So you can think of this as some kind of like information theoretic quantum advantage, or at least a proof of concept of this. Okay. So I won't describe how the lower bound was proved, but let me just describe the simple observation that leads to the upper bound. Right, so why can you get away with only n over epsilon to the 4th samples when you can measure two copies at a time? Probably many of you have seen this trick. Right, so the point is that the Pali operators themselves don't commute, but they're tensor squareds too. Right, so if I look at P tensor 2, Q tensor 2, you can easily show that these are mutually commuting. And now the point is I just work in the joint eigenbasis for these commuting operators, P tensor 2, which is just the Bell basis. And now I can, because all these things are commuting, I can very efficiently estimate these trace P tensor 2 rho tensor 2s, which is just the square of trace P rho. Okay? Now if I want to get access to trace P rho, well, I'll just square root these estimates. Of course, at this point, I lose the sign, so this was the kind of footnote that I mentioned earlier. But the upshot is if I just want to estimate the absolute values, I can just estimate these to within sufficiently good error, like on the order of epsilon squared, and out pops this order n over epsilon to the fourth scaling. Okay? So really the only trick here was the Pauli operators don't commute, but their squares commute. Okay, so we're going to come back to this epsilon to the fourth scaling because this is very different from the usual kind of parametric rate that you see in statistical estimation. Okay, and the nice thing is this is a separation that you can kind of witness even in practice. Okay, so a couple years back, we sort of demonstrated this sort of separation empirically. And the main takeaway from this whole story was that, well, here's a nice kind of simple toy task that if your quantum computer could solve efficiently, this is kind of a certificate that it actually has non-trivial quantum memory, at least enough to perform these 2-copy measurements. Okay, so this was the story from 2021. What do I want to tell you about today? Let me also briefly mention that there was some refinement to this, where instead of just looking at 1 copy versus 2 copy, you could look sort of in the spectrum in between, and it turns out you get some natural interpolation. What I want to tell you about today are some refinements to this bound that answer sort of all the remaining open questions in this landscape. So one natural question you could ask is, okay, all these rates are for estimating all Pauli observables, all 4 to the n. But in practice, maybe I only care about a specific subset of observables. Right? If I'm doing energy estimation, maybe I only care about the terms that actually appear in the Pauli decomposition of this Hamiltonian. This epsilon to the fourth is rather mysterious, and it was at the time very unclear to what extent this was just an artifact of our analysis. You could also ask, this factor of 3 here, this is maybe more of a technical question, what is the optimal trade-off between the amount of quantum memory you have, as measured by the number of ancilla, versus the number of copies you need to solve the task? And finally, what if you want the actual values, not just the absolute values? Right? So how do you actually resolve these ambiguities in sign that were introduced from this squaring trick that I showed you earlier? And so what I'll tell you about is a result that kind of allows you to simultaneously answer many of these questions at once by looking at what I call sort of an instance optimal sample complexity for shadow tomography. So let me describe what I mean by this. Okay. So here's kind of the main kind of meta theorem that drives a lot of the results in this work that address the questions I showed you on the previous slide. The setup is as follows. Let's say I care about a specific collection of Pauli operators. And because of whatever experimental constraints I have, I only care about a certain collection of measurement operations. So I have some collection of C-copy POVMs. This could, for instance, be the set of all 1-copy POVMs. But more generally, it could be the set of all, let's say, C-copy POVMs with a limited number of ancilla. Okay, these are 2 things that you get to decide: the set of Pauli observables that you care about, and the class of measurement protocols that you have access to. So it turns out you can actually pinpoint precisely what is the sample complexity for this task of Pauli shadow tomography, given any choice of A and M. So in this sense, it's instance optimal because it's adaptive to both the problem at hand, as quantified by A, and the experimental setup that you have access to. Okay? And roughly speaking, this characterization of the sample complexity has the following flavor. You can think of it as sort of a 2-player game that's going on. Right? So on the one hand, Sally is trying to pick some distribution over Pauli observables in A to stump Charlie. So she's going to pick some hard distribution over these observables. And then Charlie's goal is as follows. So intuitively, he wants to learn as well as he can over this hard distribution over observables. But his learning task is actually quite simplified. So for all intents and purposes, let's imagine C here is like 1 or 2. Okay? What is the task that Charlie really wants to do well at? He wants to find the best 1 or 2 copy POVM that can help him distinguish between 1 or 2 copies of either the maximally mixed state or this slight perturbation of the maximally mixed state in the direction of P, where P has been sampled from Sally's hard distribution. Okay? That's it. So the point is that at this point, the learning task has boiled down to just this C copy learning question, rather than one involving an arbitrary number of samples. And okay, you can make this all quantitative, but the formula here is not super relevant to the purpose of this talk. The point of this is just to emphasize that there is a formal quantity that you can ascribe to this 2-player game. Okay, so it turns out that you can actually precisely characterize the sample complexity for any choice of Pauli observables, A, and any collection of POVMs that you're allowed to perform. And the sample complexity ends up scaling inversely in this delta quantity. So just a word on the proof, although I think in the interest of time, I'll skip through this. It goes through kind of a recent refinement of this original learning tree framework that we used in our original work with Kotler, Huang, and Li. In a nutshell, the technique tries quantifying the amount of information that you learn in each step of your learning protocol, and quantifying this as sort of fluctuations of a certain quantity that's called the likelihood ratio. And the kind of key punchline behind this technique is to use the fact that these fluctuations behave in kind of a martingale fashion so that you can appeal to certain martingale concentration inequalities. Okay, so that's all I wanted to say. I think I will probably skip through this. Apologies for the. Right, so this is the kind of general architecture, but I'll skip the technical details. Great. Okay, so that's all I wanted to say about the lower bound. The surprising feature of this bound is that it actually, I went through a specific proof technique to establish that the number of samples you need is at least this quantity. But actually, it's also an upper bound, right? So actually, the upper bound is precisely captured by this quantity, suggesting that this martingale technique is actually nearly optimal. And then one final bonus is that the protocol, which I'll tell you about in a few slides, actually estimates the actual values, the actual Pauli observables, rather than the absolute values. Okay, so this characterization here is a bit of abstract nonsense, right? It's ultimately some min-max optimization. But the nice thing is that once you have this abstract characterization, you can start plugging it in to get sort of user-friendly bounds. So just as one example of an instantiation of this bound, you could, for instance, focus on measurements that are given by single-copy Clifford measurements. In this case, one very nice fact you can show is that the sample complexity for Pauli shadow tomography of some collection of Pauli observables is exactly given by a graph theoretic quantity. Right? You write down the anti-commutation graph corresponding to your set of Pauli observables, and it's the so-called fractional coloring number. Right? So I won't define for you what that is, but it's some combinatorial quantity that you can assign to any given graph, and it precisely dictates the number of samples that you need for that collection of Pauli observables. Okay. This was also obtained concurrently in this work by this nice triply efficient shadow tomography paper by Robbie King, David Gossett, Robin Kothari, and Babish. Okay, so let me tell you a bit about this aspect of learning the signs. The idea is actually quite simple, but I think the conceptual takeaway is kind of cute. Okay, so in order to achieve this kind of optimal scaling, while still recovering not just the absolute values, but the actual values of the Pauli observables, you really have to rely on adaptivity. And so here's how the protocol in a nutshell works. Let's even just focus on the case where you want to estimate all Pauli observables for this talk. Okay, so it operates in kind of three stages. Right? So the first is what's done in prior work. You just estimate all of the absolute values of the trace quantities by measuring the Bell basis. Okay. Now, how do you resolve the signs? Well, in at least information theoretically, what you can imagine doing, although there are ways of trying to achieve, achieving this algorithmically, you can imagine brute forcing for some reference state, rho hat. Okay? And this rho hat will not necessarily be your true state rho, but it's going to closely match the absolute values of rho, which you do know. Okay? So suppose you've done this brute force. Actually, in this paper by Robbie et al., they show you can do this using matrix multiplicative weights. But once you have this reference state rho hat in hand, what can you do? Well, you would like to now simulate Bell basis measurements not of rho tensor rho, as before, but actually of rho tensor rho hat. Okay? Right, so I can, in principle, try simulating Bell basis measurements of this tensored state now using just single copy measurements of rho, right? Because rho hat is a known state. You have an explicit description of it. And so there's only one copy of this unknown state rho that's involved in any one of these measurements. Okay? So at this point, you can just simulate these Bell basis measurements of rho hat tensor rho. And the point is you've gotten access now to, instead of trace of p rho squared, you get trace of p rho times trace of p rho hat. Well, you know p rho hat because you know rho hat. You also know the absolute values of trace p rho. This allows you to now resolve the sign for trace p rho. Okay? This was also obtained in this concurrent work. And then one cute fact that we observed is actually, this protocol is highly adaptive, right? Because it crucially hinges on trying to brute force for this reference state rho hat that matches the absolute values, right? And the measurement that you choose, the single copy measurement that you choose in step 3, is crucially adaptive on what you've learned in the first 2 steps. And it turns out this is actually fundamental. So if you only work with a non-adaptive measurement scheme, actually using not just non-adaptive single copy, sorry, apologies, there's a typo here. Using non-adaptive 2-copy measurements, you can't get this rate. You have to actually pay exponentially in the system size if you throw out adaptivity. Which I find interesting because this is kind of running counter to the prevailing theme over the last few years of saying that actually adaptivity doesn't seem to help that much for quantum state learning. It's usually a pain to try proving lower bounds against adaptive protocols, but generally we found that the rates between adaptive and non-adaptive seem to match. This is an example where we have a very strong separation between what you can do with non-adaptive 2-copy measurements versus adaptive 2-copy measurements. Okay? Great. So that's all I wanted to say about the instance optimal bound. Let me just briefly record some implications of this bound. Right? So going back to this bullet point list of open directions from the prior work. From this instance optimal bound, you can extract, for instance, an answer to this question of what is the right dependence on epsilon? Right? What is the number of samples I need as a function of the inverse position that I care about? And it turns out that we have the following answer. So roughly speaking, what this bound says is that I either have to pay exponentially in the system size, but if not, then I have to pay 1 over epsilon to the 4th. Okay? So I won't go into the proof. Roughly speaking, the thing that you should take away from this equation is that we have this 2-player game characterization of the sample complexity, and you can write down some expansion, some series expansion in the error term epsilon. And this 2 to the n scaling appears as kind of the first order term in this expansion, and the 1 over epsilon to the 4th appears in the second order. So this 1 over epsilon to the 4th, which kind of emerged as an artifact of the square rooting trick, is actually fundamental. Okay? And it actually also explains why many of this, essentially all the state-of-the-art algorithms for general shadow tomography also kind of run into this 1 over epsilon to the 4th bottleneck. Because even for Pauli shadow tomography, if you only work with C, which is like of order poly n, you have to pay this 1 over epsilon to the 4th if you want to avoid exponential scaling. You can now subsequently refine this bound. So instead of working with 1 or 2 copy measurements, you can also work in the setting where I just have a bounded number of ancilla. And actually, with this machinery, you can now get kind of the optimal interpolation between the number of ancilla and the number of copies. Okay. So let me kind of end with some sort of bonus observations that suggest that there's more to be said than just this landscape of 1 or 2 copy measurements. It turns out that actually, even for general shadow tomography, this 1 over epsilon to the 4th issue does go away at some point. What you can show is that if I'm allowed to actually make collective measurements that are entangled across now actually square in the Hilbert space dimension, so very, exponentially many copies entangled together, you can actually avoid this 1 over epsilon to the 4th scaling. And in fact, you can get all the way down to the optimal log m over epsilon squared rate, with the caveat that this result applies in kind of the high accuracy regime, where the error to which you want to estimate your observables is scaling inversely in polynomial in the Hilbert space dimension. Okay. The main takeaway here is that if you go significantly beyond this kind of 1 or 2 copy picture, you can get very different looking statistical rates. And so I won't say much about the proof, but also remark that actually, interestingly, it's still open. If you lift this caveat about epsilon being at most 1 over poly d, it's still open what the optimal rate for shadow tomography is for general observables. Okay. All right, let me skip this. And then one last bonus result, just to kind of convince you that this picture extends well beyond kind of shadow tomography. Here's another result that you can show using related techniques in our work. So you can also consider the following toy task, and this is one of the other kind of proto sort of memory sample trade-offs that was shown in this earlier work joint with Kotler, Huang, and Li. Consider the following task. I give you a bunch of copies of rho, and I promise you it's either maximally mixed or it's pure. Okay? And you just have to say yes, which one is it? So if you have no quantum memory, it was shown previously that you need to pay exponentially in the number of qubits if you're working with single copy measurements. Of course, if you're working with 2 copy measurements, you can just run swap test. But now you can also ask this question, if I have just an intermediate number of ancilla, what is the right statistical rate? And what's interesting about this task is actually you see this weird phase transition that happens depending on how much memory you have. Okay? So if I plot on the x-axis the number of ancilla I have, right, at the extreme, if I have n ancilla, I can just run swap test and everything's fine. At 0, the log of the sample complexity is n over 2. So you just track this orange line, this orange dotted line. And what you see is actually as long as you're below half as many ancilla as you would need to run the swap test, you can't beat the single copy algorithm. Right? You're still stuck at 2 to the n over 2. But as soon as you exceed n over 2 ancilla, it starts dipping below, right? and smoothly interpolating towards swap test. Okay? From a technical perspective, it's interesting in that some of these martingale techniques that I mentioned actually aren't sufficient to get the result. You have to go kind of beyond this, but I'll skip that for today's talk. Okay. Right. Let me now move on to the second part of today's talk, and this is on magic estimation. Right? So previously, we were focused on this question of estimating Pauli observables. Now let's go to a question which actually can be still framed within the perspective of shadow tomography, but for a different class of observables. Right? So here we're going to estimate the stabilizer fidelity, right? The max over all stabilizer states of the fidelity between your unknown state row and your stabilizer state. Okay. Also, how am I doing on time? 5 more minutes. Okay, sounds good. Great. Okay, let me try maybe just mentioning some of the punchlines. Okay, so let me just introduce some basic preliminaries. Okay, so we all know what stabilizer states are. These are highly entangled but classically simulable, and this is the notion of magic that we want to target. Okay, so this is something you could easily do with classical shadows if you don't care about runtime and you only care about sample complexity. You can just imagine while you're taking a maximum fidelity across an entire collection of pure states. Right? Those are your observables, the projectors to in the directions of each of these pure states. And with classical shadows, because there are 2 to the order n squared many stabilizer states, you can get an estimation for all these fidelities in a number of samples that scales only polynomially in n. But unfortunately, to turn this into an algorithm, you would still have to brute force over all stabilizer states. So you would still pay exponential in n. And indeed, the conventional wisdom is that this notion of magic is not very user-friendly because it involves optimizing over exponentially many stabilizer states. Okay? So I'm going to give you kind of a sketch in the remaining time of how this algorithm works. But actually, we're going to estimate magic by passing to an even more challenging task, which sometimes is called agnostic tomography. The basic premise is instead of trying to estimate max, I'm actually going to try estimating the argmax. I'm actually going to try finding the stabilizer state that's closest to my candidate state. And if you have this, then you get a bunch of consequences downstream. You can estimate magic. You can solve the stabilizer testing or tolerant stabilizer testing problems that have received attention in the last few years. So this is a great algorithmic primitive if you have it. Of course, it's not a priori clear that this is possible computationally efficiently. Okay. So in the case where the state is actually promised to be a stabilizer state and you just want to find it, right? That's the special case of agnostic tomography where the stabilizer fidelity is 1. Then it's been known for some time that you can learn stabilizer states, of course. One popular primitive for this is something called Bell difference sampling. I'll skip the preliminaries because probably many people are familiar with this. The basic idea is that you have some unknown stabilizer group of the state that you want to learn, and you just run some particular measurement protocol called Bell difference sampling that effectively gives you uniform snapshots of this stabilizer group. Okay? Once you have the stabilizer group, the rest is easy. The issue is that if the state is not exactly stabilizer, these draws given by Bell difference sampling are going to kind of fall off of the subspace corresponding to your stabilizer state. And classically, the intuition is that once you have kind of noisy linear subspace problems over finite fields, you get computational hardness. Indeed, it's unclear in this quantum setting whether Bell difference sampling can do anything useful as soon as you work with a stabilizer state, maybe plus some constant amount of noise. Okay, so let me skip to our results. Kind of the main finding that we have is that actually there is an algorithm for this task, and its scaling is quasi-polynomial in 1 over the stabilizer fidelity of the unknown state, but actually polynomial in all of the other parameters. And in fact, we give a general framework called stabilizer bootstrapping that works not just for stabilizer states, but also for, it gets kind of new results for a variety of other kinds of states. And okay, I'm running out of time, so let me just say briefly the general recipe. Oh, okay, great. Okay, that's great, actually. So then I should be able to actually describe this entire slide and conclude. Okay, so let me quickly go over the outline of the algorithm. Okay, so it's sort of it operates in a bunch of rounds, where in each round there are sort of 4 steps. Okay. Okay, so the first step, what you're going to do is you're going to try running Bell difference sampling to collect a bunch of pallies that maybe are in your stabilizer group, maybe they're not. Okay? But you only keep the ones that have high correlation, in the sense of trace p rho squared, with your unknown state rho. Okay? So you gather all these high correlation pallies, and by uncertainty principle, these will commute if they're all of sufficiently high correlation. You go to step 2, and you say, well, if they actually generate the stabilizer group, then we're done. Okay? If they don't, then we have to recurse and somehow make progress. And here, we're simply going to do the following. We're going to do Bell difference sampling one more time and collect a pally that we hope has low correlation with our unknown state rho, and furthermore lives inside the stabilizer group. Okay? And based on what we know about Bell difference sampling, actually, there's a non-negligible chance that you successfully produce this low correlation pally. Okay? So the main point now is that I have access to a pally in the stabilizer group, provided all of these steps worked, whose trace against, so for which trace of p rho is upper bounded, okay? is not too large. The key step, and this is where, again, adaptivity kind of rears its head, is to do the following bootstrapping step. Let's imagine actually taking that pally and measuring with it. Okay? Suppose pi is the projector to the pally that actually stabilizes psi, and let's look at the post-measurement state resulting from this measurement. Okay? Let's call this rho prime. Okay, so the key observation is just a single line, right? It says, let's look at the fidelity between my post-measurement state and this target stabilizer state psi. Okay, so I can rewrite this as the second expression. The point is that my projector stabilizes psi by design. And furthermore, the denominator is not too large, right? So the denominator is upper bounded by, let's say, 0.9, right? Which means that you can lower bound this whole expression by the fidelity between the unknown state and the stabilizer state times a constant factor that's larger than 1. So this is the bootstrapping step. This allows you to now go from rho to rho prime, for which the fidelity with respect to this unknown stabilizer state actually increases by a constant factor. Okay? So if you've made it all the way to this step in the algorithm, now you can just recurse, right? I've boosted my stabilizer fidelity. I'm no longer working with rho, I'm working with rho prime. I've boosted it by a constant factor, and this can only happen a logarithmic number of times. Okay? And that's the entire punchline. Okay, so the main thing I should mention is that, of course, all of these steps hinge on the previous steps working out. The point is that each of these steps has a small but non-negligible probability of success. And so what you do is you simply repeat this algorithm, many traces of this algorithm, where by many, I don't mean exponentially many, but only, in this case, quasi-polynomially many in 1/, stabilizer fidelity. And at the end, you get a bunch of candidate stabilizer states. And at that point, you can do some kind of hypothesis selection, right? The set of stabilizer states is not too large. You pick the one that has largest fidelity with your unknown state. And that's the whole algorithm. Okay, so let me conclude with some general takeaways. Evidently, sidestepping this classical desideratum of full state tomography gives you access to a very rich landscape of algorithmic questions to study. In the first part, we saw kind of a very interesting interplay between the role of memory and the role of information in quantum learning. And in the second part, probably the most surprising aspect of this algorithm for estimating stabilizer fidelity is that it looks, the picture looks very different qualitatively from what happens classically. Classically, once you have noise, these kinds of discrete learning problems become hopelessly hard. But somehow, quantumly, the magic of Bell difference sampling gives us access to quite efficient learning protocols. What we saw is that Bell sampling is this very universal trick that appeared in both parts, but only with these careful adaptive tweaks. In the first part, this kind of sign extraction protocol, in the second part, this bootstrapping method. These careful adaptive tweaks are essential to getting the actual boosts that I mentioned in this talk. Some of the stuff I mentioned in the first part suggests that going beyond 2-copy measurements, there's a lot still left to be explored. So I'll just end with kind of an open note. So at this point, I think we understand stabilizer-based or Pauli-adjacent kind of learning questions quite well. But beyond the setting, we actually don't have much. Right? As soon as you lose Bell difference sampling, it's not really clear what to do to get kind of comparable guarantees. And so some concrete open questions that are left include things like trying to understand agnostic tomography for other classes of states, Gibbs states, bounded depth circuit states. And as I mentioned, kind of this guiding question at the beginning still remains frustratingly open. For general observables, can you get optimal rates and efficient algorithms for shadow tomography? Right? So that's all I wanted to talk about. Thanks so much for listening.
Thank you so much for the talk, Sitan. We have time for questions. Okay.
So like when you use the martingale concentration, you can get a very small constant factor in the lower bound. So like I wonder how hard it is actually in practice.
Oh yeah, this is a great question. This is a very this is some insider knowledge about the martingale technique. So unfortunately, for whatever reason, and it might be fundamental, the martingale technique ends up introducing a very impractical absolute constant factor in front of the lower bound. I think the reason is because a lot of the arguments actually use sort of like Markov style, like first moment style arguments to kind of truncate away bad events in the decision tree. I suspect that maybe with like finer grain, like higher moment information, you can get better constants. But yeah, we never tried drilling into this, but we really should. Yeah, it's a great question.
Thanks for the nice talk. What do you learn about the stabilizer? I mean, the stabilized state, like classically. I mean, what type of information do you learn?
So you get a description of the stabilizer group, and so an explicit description of the underlying stabilizer state that's closest up to this error, right? So you don't, it's not literally argmax, but it's going to be, so I kind of flashed through the definition. You get access to a stabilizer state whose fidelity is epsilon away from the stabilizer fidelity. Yeah, so that's, yeah.
Hey, great talk. So the answer to this is probably going to be, I don't know, but I figured I should ask anyways. I'm kind of curious, have you thought about looking at the CV analog of stabilizer states, specifically Gaussian states here, and whether or not some of these ideas could be evolved in order to do the same thing for oscillators, say?
I mean, the short answer is indeed, I don't know. I think maybe one challenging thing is, maybe this is just my ignorance, it's not clear what, I guess, the right analog of this Bell difference sampling trick is. So, but I think this is really crucial for instance, even in the qubit setting, I have no idea how to do this with get anything interesting with single qubit, single copy measurements. Whereas, for learning stabilizer states in the non-agnostic setting, of course, we have algorithms based on computational difference sampling. It's actually not clear how to get any of those methods to interface with the bootstrapping. But it's a fantastic direction, yeah.
Thanks for a nice talk. So you mentioned this very nice property of noise robustness in this quantum algorithm for this quantum learning task. So do you envision this being generalizable to some classical setting as well? Like, for example, using a quantum algorithm for classical learning tasks?
Yeah, it's very mysterious to me. I mean, this is the only example I'm aware of. My sense is that I think when we started this project, the thing that I was pessimistic about was, of course, even in the original kind of noiseless learning stabilizer state algorithm that goes, let's say via the Bell difference sampling stuff, at the end you have to do some kind of Gaussian elimination to sort of figure out the actual generating set for this. For the stabilizer group. And the pessimistic part was, okay, once you have Gaussian elimination and you have noise, you're kind of toast. My understanding of what this algorithm is really doing is it's still offloading the classical computation, this hard, fine-grained procedure of Gaussian elimination to the classical algorithm, but it's ensuring that kind of the classical post-processing never has to interface with the noise. So somehow the only role of the quantum part of this algorithm is to clean up the noise to present what classically you would have seen in the non-agnostic setting. And I don't know more generally if this phenomenon happens anywhere, but yeah.
Thanks. Okay, let's thank Sitan again.
Thanks, Mike.